Okay, so last time we provide the questions. That is what's the problem of the Petrov equation? What's the assumption of this Petrov equation? Well, the assumption of the Petrov equation is that we assume the clearance between the journal and no, the journal and bearing, the clearance, the C, where the C is constant. Okay, C is a constant. However, in the real case, C, the clearance is not a constant, right? If you still remember, there's a wedge shape uh, due to this pressure, right? We'll create the pressure distribution to support this journal, right? Therefore, the clearance is not fixed. It's not fixed. Well, however, it doesn't mean this Patrick equation is meaningless. Well, we still use it to evaluate the different parameters, and we still use it to create the chart and tables, okay, for the future uh, lookup, okay? So you will see some chart tables in the textbook or handbooks, and those parameters are based on the Patrick's equation. Okay, Patrick's equations right here. Okay. Okay. So let's see the Patrick equation. If we can reorganize it, there's two terms. One is the R, the radius of the journal divided by the clearance, R over C. And the other parameters are the mu times the N is the RPM per pressure, right? The pressure applied to the journal, right? So we have two parameters, remember. So you guys have to remember these two parameters first. Okay. Okay, so if we plot this figures of this friction coefficient corresponding to the bearing modulus. Okay, so what is the bearing modulus, right? The bearing modulus equals to mu n divided by the pressure, right? So if you still remember the Patrick's equation, right? From this Patrick equation, right? So this term defines the bearing modulus, okay? Defines the bearing modulus. Okay, so if we plot those figures related to the friction coefficient corresponding to the bearing modulus, we'll see. So what's this figures tells us? Okay, so there's a limit at this AB line, the dotted line, AB. Okay, so the left side of the AB, that's mean the clearance between the journal and bearing is very thin. As this clearance becoming thinner, that's mean it is unstable. And what happens? What happens if this bearing modulus is a left of this AB limit? Okay, that means this clearance is become thinner and thinner, right? So that means the friction and create more heat due to the temperature rising, right? So if you still remember, as the temperature rising, the viscosity of this oil, this lubricant, will getting lower, right? And this viscosity of the lubricant become lower, and this clearance become thinner. And become thinner, that means the friction increase and more heat again and again. It's a crisis loop. It's a crisis loop if we design the journal bearing whose thickness, the thickness is in the left of this AB boundary. Okay. On the other hand, if we design the clearance, we design the bearing modulus. It's located at the left, at the right of this AB limit. That means the clearance, the thickness of the clearance is getting thicker. We get a thick film. That means the lubricant is stable. So you have to remember there's a limit AB boundary. If on the left of it, that means we're getting thinner film to create higher friction, higher temperature, and lower viscosity. On the other hand, if this is a thick film, that means we have this lower friction coefficient, lower friction coefficient. Okay, therefore we can reduce the heat, reduce the friction, right? Therefore, this higher viscosity of the lubricant, Therefore, there's a limit. Okay, there's a limit based on the experiment data. Okay, based on experimental data. Okay. Okay, so any question of that? Okay. Okay, so if this thin clearance, these two surfaces almost contact, right? And when these two surfaces contact with each other, the friction increased, temperature increased, right? And for the thick lubricant, and these two surfaces are separated stably, therefore, this journals keep rotating with relatively lower temperature. Okay, relatively lower temperature. Okay. Okay, so this is what I already talked about previously. Okay, to the left of the AB, changes in conditions are self-correcting and resulting in stable lubricant. To the left of the AB, changes in conditions tend to get worse and results in unstable lubrication. And point C presents the proximate transition between the metal to metal contact and thick film separation of the parts. Okay, common design constraint for point B. Okay, and if the bearing modulus is to be the left of the AB, what happens? Okay, that's I already mentioned, right? So the thinner the contact, metal to metal contact, that's mean the higher friction energy created. That's mean the higher heat created. And higher heat created, that's mean higher temperature causes the low viscosity of the lubricant. Okay, so this is what I mentioned previously. Okay, so let's go back to the this Patrick's equation, right? So this term it defines the the bearing modulus, okay, the bearing modulus, and R over C is the radial clearance ratio, okay, radial clearance ratio. Okay, now we define the other parameters called the Sommerfeld number or the bearing characteristic number. S is the square root of the radial clearance ratio times the bearing modulus. Okay, times the bearing modulus. Okay, and intersecting the relation from multiply the equation by R over C. That's mean you can multiply by the R over C, right? Both on the left and right. Okay, so we got this equation, right? Both times the R over C, R over C. Okay, and this term equals to 2 pi squared times S. S is defined as the Sommerfeld number. Sommerfeld number. Okay, Sommerfeld number. Okay. So any questions? Okay. Okay, so we can figure out a chart with the this Sommerfeld number with respect to the F, the friction coefficient times the radial clearance ratio. Okay, the radial clearance ratio. Okay, with the different L over D value. L over D, L is the length of the bearing, the bushing. Okay, and the D is diameter of the journal. Okay, diameter of the journal. Okay. Okay, so as I mentioned previously, the journal bearing, the clearance is not a constant. Okay, it's varying during rotation, right? During rotation. Okay, so let's focus on some nomenclatures of the journal bearing. Okay, so first is the center of the journal, C, right here, and the center of the bearing, O prime, right here. Okay, and this eccentricity, E. Okay, that's mean the distance between the O and O prime. Okay, and the radial clearance, C. Okay, is difference of the journal and pushing radius. Okay, so it's a constant. Currently, it's a constant. Okay, so remember the clearance C is a constant. However, the distance between the journal and bearing H is a variable. Okay, it's a variable. Okay, so the minimum film thickness H naught occurs at the line of center. So what's the line of centers? Line of centers is the direction along with the O and O prime. Okay, so this is the line of center. Okay, therefore the minimum film thickness H naught occur at the length of center. Okay, right here. Okay, and the film thickness anywhere is H, right? So H is a variable, and H equals to C, the constant, the clearance C, plus the E is a eccentricity times cosine theta. Cosine theta. Okay, E times cosine theta. That's mean the anywhere. Okay, the anywhere. Okay. Any questions on that? Okay. And the steady load W applied to the general bearing, right? CW, the counterclockwise at the steady speed N, RPM. Okay. And there's a constant steady load W, or say the weight of the journal. Okay. And the altitude angle phi, where's the phi here? Is the angle between the eccentricity and the load vector. So eccentricity whose vector is along the O and O prime, right? O and O prime. And the load vectors, right? As W, right? W. Therefore, the angle between them, okay, defined as the attitude angle, phi. When a lubricant is introduced at top, the rotation pumps the lubricant into a converged wedge-shaped space and forces the journal center to a steady position to the side. Okay, so the lubricant is introduced, right, from the top. Okay, introduced at the top, and the rotating pumps the lubricants into a convergent wedge shape. So this rotation is pumping this oil, this lubricant into a convergent shape. Okay, so when this journal keep rotating, it will pump to make a converging shape. So what is a converging shape? It's like this. I will draw. Okay. So this is the converging shape. Okay, it's a converging shape. And this converging shape provide the pressure, provide the force. Okay, provide the pressure, forces the journal center to at the steady position. Okay, so this journal will keep at the steady position due to this wedge shape. Its wedge shape of the of this oil and produce the pressure. This pressure forces this journal fix at the steady position. Okay, at a steady position. Okay. Okay, and the minimum film thickness H naught occur not along the load line, but at the point displaced clockwise from the load. Okay, H naught right here, right here, which is not along the load line. This is the load line, right? So from the theory, from our common senses, we'll feel okay. So the minimum film should be along the load side, right? Because the load direction is downward, right? So obviously, or from our common sense, this minimum gap should be along the load line. However, it's not. Therefore, the minimum film thickness not along the load lines. Okay, not along, but a point displaced clockwise from the load. Okay, clockwise with a theta phi. Okay, with a theta phi. Right, counterclockwise with the angle phi. Okay, and the load is supported in a region of complete lubricant film from the inlet region to a point just beyond the minimum film thickness. Okay, so the load is supported. It's supposed this journal in a region. Okay, so what the region? Where's the region? Where's the region that I mentioned? I already mentioned previously, right? So we have this oil coming in right here, right? Oil coming in right here. That's mean from the inlet region, right? To the point just beyond the minimum film thickness. So this region, I plugged it, this region, this is the convergent region, right? As I mentioned previously. So this convergent region support right? It support the load or suppose the load W, right? This region supported. Okay. As the journal and the bushing surface diverge, result in a significant pressure drop. Okay, so when as the journal and the bushing surface diverge, result in a significant pressure drop. So as I mentioned previously, this point, this supported region is just beyond the minimum field thickness, right? So here's the minimum field thickness. Okay, so from this at the start point of the diverge region. So in this region, this defines the diverge region, right? It's diverge. Okay, diverge region. Okay, diverge region. So converge region. Okay, this is a converge region and diverge region. Okay, diverge region. Okay, with a significant pressure drop. Okay, so that's mean. Let me change your color. This convergent region has the higher pressure than that of the divergent region, right? Divergent region. Okay. That's the reason why this journal can be supported. Okay, can be supported. Okay, and the fluid film ruptures or cavitates into liquid streamers separated by a liquid gas mixture. Okay. Okay, so let's look at some fluid mechanics. So if you have already took the fluid mechanics course, so I will just briefly introduce it. Okay. If we look into the film with an infinitesimal element, dx dy, the 2D element. Okay, the 2D element. The top of it is a rotating journal, and the bottom of it is a stationary partial bushing, right? And this is infinitesimal 2D element with the dimension dx and dy. Okay, so we have the pressure in x direction, right? In x direction. So on its right side is P, the pressure times the dy dz, right? Suppose we have the thickness. Okay, these, right? Okay, so we have the coordinate with x, y, and z. Okay, therefore have the force P, Y, Z. Okay, and there's a pressure difference, right, between this dx. Therefore, we still have the pressure applied at the left of this 2D element, right? That's the P plus the dP dx times dx times the area dy dz. And similarly, there's a shear stress on the top and bottom. Okay, shear stress top and bottom. Okay. Okay, and therefore we can just work on this the force equilibrium, sigma fx equals to 0. Right? Sigma fx equals to 0. Sigma fx, the shear, right? Top and bottom equals to 0. Okay. Okay, so any question on that? So we can manipulate this equation, right? And the P dx, the pressure, take the derivative of the pressure P with respect to x, will equals to the partial derivative of the tau, the shear stress divided by y. Okay. Okay, so you can just keep this P on the left and the tau to the right, so we can figure out this relation. Okay, so from this previous lessons, we already know the tau equals to this mu viscosity times the velocity gradients along the y direction, right? So we can plot this term here, right? So we got this derivative of the pressure with respect to x equals to mu times the second partial derivative of the u over the partial derivative of the y squared. Okay, y squared. Okay, and then we can solve this ODE and PDE questions, right? So we got this partial u partial y equals to the 1 over viscosity times the dP dx times y plus the constant, right? Plus a constant, okay? And then we can just take the integration on both sides. So we get this relation of the u, the velocity, right? Corresponding to the pressure gradients and y. Okay, so how to solve the C1, C2? How to get the C1, C2? Boundary condition, right? Boundary condition. Boundary condition. Therefore, we get this y equals to 0, u equal to 0, right? And y equals to h, the u equals to the capital U. It's a constant velocity, right? So we get this constant c equals to this term, and the C2 equals to 0. And we plug C1 and C2 in the previous equation, and we get this U, the velocity profile. Okay, the velocity profile along the y direction. The y direction is we say the h. Okay, the valuable thickness, the film thickness between the journal and the bearing. Okay, the journal and the bushing. Okay. So any questions? Okay, so we got this profile, the viscosity profile. Okay, say the viscosity distribution superposes parabolic distribution onto the linear distribution when pressure is maximum. Okay, that means the dpdx equal to 0 and the u equals to the capital U divided by h times the y. Okay, times the y. That means when this pressure gradient dpdx equal to 0, the velocity profile, we'll say the velocity distribution is parabolic, right? So when this dpdx equal to 0, this velocity distribution, it's linear. Okay, it's linear. Okay, when the dpdx equal to 0, this distribution, velocity distribution, is linear. Okay. Okay, so it's linear. Okay, so the distribution U with respect to the y is linear distribution when the dpdx equal to 0. Okay. Okay. Similarly, when this dpdx is greater than 0 or the dpdx is less than 0, we'll get parabolic. Okay, parabolic. Concave and convex is a parabolic. Okay, distribution, parabolic distribution. Okay. Okay, the flow rate Q. Okay, flow rate. The classical Reynolds equation for one-dimensional flow, ignoring the side leakage. Okay, so this is the Reynolds equation. We already know it, right? Okay, so with the Q, the flow rate in one dimension, right? So the U, the velocity profile, the velocity distribution times the dy, and take the integral from the 0, the clearance from the 0 to h. Okay, and we get the Q, right, equal to U, capital U h divided by 2 minus this term. Okay, and we take the derivative of the Q, the flow rate in one dimension, with respect to x equal to 0. So we take the derivative of the Q with respect to x equal to 0. Right, we'll get this equation. Okay, we'll get this equation. Okay. So this equation defines the Reynolds equation for one-dimensional flow, ignoring the side leakage. Okay, and if this journal bearing with the leakage, okay, with the leakage, this equation have to be modified. Okay, have to be modified. This equation is the Reynolds equation without leakage, and with side leakage included, the Reynolds equation for 2D flows will be modified as this equation. Okay, so we have to turn in z direction. We have to turn in z direction. Okay, we have the leakage in z direction. I'll just mention this maybe later or next chapter, next time. Okay, and for the partial curve, bearing. That means it's not the whole journal bearing, it's just partial. Okay, just partial of it. Okay, just partial of it. We just replace the x with the r theta here, and the u, the velocity, equals to r omega. Okay, so we can just replace this here, here, and here, right? So we got the curved partial bearing whose Reynolds equation, okay? Whose Reynolds equation, okay? Okay, and Albert Remedy and John Boyd used an iteration technique to solve the Reynolds equation, okay? And published 45 charts and tables, okay? And this text includes charts from parts of the Remedy and Boyd, okay? So these two guys use the iteration technique to solve this Reynolds equation, okay? And make the tables and charts, okay? I will just introduce the table and chart later, okay? Okay, and when, as I mentioned previously, we have this converging and diverging region, right? So we can plot this converging region with its pressure distribution. Okay, pressure distribution. And there's a maximum pressure occurs somewhere. Occurs somewhere. Okay, occurs somewhere. Okay, so there's one example here. So I think I will skip it. You can just work on it for yourself. Okay. So after you finish these examples, you'll realize more. You'll understand what I'm talking about. Okay. So you can skip it. Okay, so this is the one of the charge from the remedy and the board. Okay, so similarly, this x-axis represents the this Semmelweis number, and the y is the h naught over c. So all these curves are created from experimental data. Okay, and the L over D is the length of the bushing, and D is the diameter of the journal. Okay. Okay. Similarly, we have worked on the different charts. Still, this x-axis represents the Semmelweis number, and the y is the phi. Okay, the position of the minimum film. Okay, position of the minimum film, and this chart represents the Semmelweis number, right, corresponding to the radial clearance ratio times the friction coefficient. Okay, friction coefficient. Okay, and this is evaluate the Semmelweis number with respect to the flow rate, the flow variable. Okay, and with the geometry design of the journal and the bushing. Okay, similarly, the Semmelweis number with the flow ratio, the QS and the QS is the side leakage volumetric flow rate. Okay, and this defines the Semmelweis number with the minimum film pressure ratio. Okay, the pressure ratio. Okay. Okay, this chart represents the bearing characteristic number, Semmelweis number, with respect to the determining position of the film. Okay, of the film. Okay. Phi naught. Where's the phi naught is? Right here. It's the phi naught. Okay. Okay, that's mean the pressure start to decrease, which is not, no, the pressures gradually decrease, which is the angle between the load vector right? And the pressure will end it at this point, at this location. Okay, so this at this location. Okay, and we define the determining pressure, right, at the angle phi naught. Okay, that means you will get the zero pressure at this point. Okay, at this point. Okay. Okay, so I just quickly go through this figure. Okay, so the Q is the flow rate. Okay, that means the lubricant be pumping inside the film, pumping inside the clearance between the journal and the bushing, right? And it will return to the oil pan. It will return. It's the inlet and outlet. So it's a circulation from where you filled in the lubricant to where this oil return. Okay. So previously we mentioned some cases without the leakage, right? Without leakage. And in general, or we say some gearbox, the gearbox be used for a long time, they must have some leakage from the Z direction. So this turn, this is the Z direction with the leakage of the volumetric flow rate QS. Okay, so suppose we have the sub is defined as the oil pan. That means the return oil will go into the sub and circulate it and keep circulating. Okay, keep circulating. Okay, keep circulating. Okay, therefore, the QS leakage will goes to we are going to the sub, the oil pan, right? And what else? The QS and the return, oil return, right? QS and oil return, right? These two type of the oil, the two type of oils will return to the sub, return to the oil pan. And then we will pump the oil to fill the lubricant again. So it's a circulation. It's a circulation. Okay, it's a circulation. And with this process, this circulating, heat will lost. Heat will lost. Okay, heat will lost. Okay, so I think I'll stop here. Okay, so I'm gonna introduce how this heat lost due to this volumetric flow rate next time. Okay, next time.